Okay, we're off to chapter 6, I believe, right? We finished up 4 last time when we were all together, if I'm not mistaken. So as I mentioned before, we're going to start here with the bonding part of this chapter with everybody here together. So this is sort of the second half of the notes from chapter 4 there. And like I said, we'll pick up the naming or continue the naming after this here. So we're going to talk about chemical bonding in this chapter, and there's really kind of 2 types of bonding that we come across, and it is really these 2 types. It is an ionic bond, and in an ionic bond, it is always between a metal and a non-metal. And always what happens sort of in an ionic bond is the metal will transfer electrons over to the non-metal. The result of that is the metal will then become positively charged, or a cation, which has a positive charge. Non-metal will pick up the electron, say thank you, and become an anion, which is negatively charged. And it is the attractive force between those 2 that actually hold that together. So it's really important to remember, in an ionic bond, there's absolutely no sharing of electrons that are happening here. It is held together by this electrostatic attraction. Basically, opposites attract. No sharing of electrons. And that's a little bit different than what we're going to talk about as well here, which is a covalent bond. In a covalent bond, that is usually between 2 nonmetals. And because the nonmetals basically share very similar sort of periodic properties, what happens is when 2 nonmetals get together, they both essentially want to hold on to their electrons, and they actually want other people's electrons as well. So the best that they could do is decide we will actually kind of share electrons here. So there's sharing of electrons that occur in a covalent bond. And as we'll talk about here, it may be equal sharing of those electrons or unequal sharing. But there is some aspect of sharing that is going on when you have a covalent bond, and that again is very different than an ionic bond, where frankly there is no aspect of sharing happening there. There's a complete transfer of electrons from one to the next. Any questions on that there so far? And obviously we'll talk more about this as we go through this part of the lecture here. So one way that we can represent bonding, both ionic bonding and also covalent bonding, is through the use of Lewis dot symbols. Some people nowadays just generically call it electron dot symbols, same thing. And the deal is with bonding, pretty much it is only the electrons involved. So if you think about sort of the model of the atom that we talked about, the electrons are on the outside of the nucleus flying around. So when 2 atoms come together, it's really those electrons that come in contact with one another first, and they are involved in bonding. More specifically, when we talk about bonding, it is only a certain type of electrons that are involved, and it is only the valence electrons that are involved in bonding. And if you remember, we talked about valence electrons. They are the outermost, highest energy electrons. And remember that pretty much the easiest way to figure out the number of valence electrons is it equals the group number. So whatever the group number for those particular elements are, that is how many valence electrons there are. So the valence electrons equal the group number on the periodic table. The other type of electrons, you remember, I think when we were talking about electron configuration, they're referred to as core electrons. Those are the ones that are closer to the nucleus. They're actually held a lot tighter because of that. So they're harder to remove or share because they're really held really tightly to the nucleus. So it's really just those outer ones that are further away from the nucleus, not held as tightly, they're able to really participate in bonding. So we use Lewis dot symbols to basically represent bonding. A Lewis dot symbol is frankly the symbol. And basically one dot to represent a valence electron. Is there rules for putting the dots on? Not really, I don't think. The only real rule is don't go more than 2 per side is usually the rule. That means since there's 4 sides and 2 electrons per side, max would mean a total max of 8 electrons. And the whole point of all bonding, as we'll talk about in this chapter, is all for everybody to pretty much get 8 electrons around them. Who on the periodic table has 8 valence electrons? The noble gases. And that is the ultimate goal of bonding, is for everybody to achieve the noble gas configuration in terms of their electrons. Again, we're not turning these elements into noble gases, but they end up becoming the same in terms of how many electrons they have. And since that's all involved in bonding and all that, that creates a nice stable arrangement for everybody to be in. And they achieve it a couple of different ways, depending on the type of bonding that occurs. And we'll talk about it depending on if it's ionic bonding versus covalent bonding, as to how they basically achieve that. That was a good slide there. So here's some Lewis dot symbols of all the representative elements. And again, you can see everybody in group 1 has 1, 2, 3, 4, 5, 6, 7, 8. A couple of reminders. First off, helium, it is part of group 8, but once again, helium only has 2 total electrons. So that's why it has only 2 valence electrons. It can't have any more than what it has. But everybody else there in group 8 does have 8 valence electrons. And as we mentioned, you don't have to worry too much about transition metals. So, you know, these are usually our representative elements here. So we're going to first talk about ionic bonding and how ionic bonds are formed. So these Lewis dot symbols really do help us understand bonding, really both types of bonding. We could use them to basically describe how an ionic bond is formed. We could also use them to describe how a covalent bond is formed. The general rules are things with low ionization energy will tend to form cations. If you remember, ionization energy is the energy required to remove an electron from the gas phase. So something has really low ionization energy, it doesn't take a lot of convincing for the electron to go. Typically on the periodic table, left and down is low ionization energy. So that's a lot of your metals. And so that's what I was saying earlier. Metals are like, you know, go ahead, take my electrons. I don't really care that much about it. Things with high electron affinity. Electron affinity is, again, the energy change that occurs when somebody gains an electron. So that's the energy change when someone, I guess that's scientific, gains electrons. Obviously, if you have an affinity for something, you like it, right? So that's another way of looking at it. They kind of like electrons. They like to gain electrons. The general trend for that is it increases as you go up and to the right on the periodic table, which is where our nonmetals are. So again, our nonmetals typically like to gain those electrons. Our metals like to not really hang on to electrons. So our nonmetals typically form negatively charged ions, and our cations, which are our positively charged ions, are usually come from our metals. So the general rule tells us that things in group 1 and 2 will form our positive ions, and things like the halogens, oxygen, all of our nonmetals there on the periodic table will essentially form our negatively charged ions. All right, so let's take a look at an example of an ionic bond. And by the way, we know it's an ionic bond for sure as soon as I identify these 2 things. And if I identify lithium, that is a metal. And fluoride is a nonmetal, which is fluorine. As soon as I see that combination, no matter what the situation is, it's just scream to you ionic bond. Yes, so it's always going to be an ionic bond. And again, we're going to have transfer of electrons here that's going to occur as a result of this. If we look at the electron configuration for each of these guys, that is lithium. which is 3 there, which is 1s2, 2s1. We have fluorine, which is 9, 1s2, 2s2, 2p5. Lithium is group 1 on the periodic table, which means if I draw this Lewis dot symbol, it'll look something like this. Once again, with this configuration, 1s2, 2s1. By the way, that is the 1 valence electron there that we're talking about. And if we put that with our fluorine, which has 7 valence electrons because it is group 7, with this configuration of 1s2, 2s2, 2p5, the 7 valence electrons being 2 and 5 is the 7 that come from there. What's going to happen when these two guys get together is, because the metal there has all of those periodic properties to say, take my electrons, and the fluorine, which is a nonmetal, has all the properties to say, I will take your electrons. The electron goes from the lithium to the fluorine. The result of that is lithium has now lost an electron, and it's at this point it becomes positively charged because it lost an electron. The fluorine in this case started with 7 electrons. I'll make it a different color here. And it picks up that 1 electron from the lithium, and it now gains a negative charge in this case. And that is the correct sort of Lewis structures to represent the ionic bonding that's happening here. A couple important aspects of the picture there on the right. They are ions, which means they should have charges. So that's why the plus is written in there and the minus is written in there. In some cases, people put brackets around both, or at minimum, at least the negative guy, to indicate that there is no sharing of electrons that are happening here. So when you draw something that's an ionic compound like this, a formation of an ionic bond, when you get to the right-hand side, like I did there, you should include charges and usually bracket up at least the negative guy there to indicate that there is absolutely no sharing of electrons happening. Now let's talk about what happens with the electron configuration here. Essentially, my lithium gave away its 1 valence electron, which means when it becomes lithium with a +1 charge, its new configuration is 1s2. The fluorine said, thank you very much. I actually have room for that guy right there in my p subshell, because the p subshell could hold 6 electrons, right? And it only's got 5 at this point. That then gives the fluoride here with a -1 charge and a configuration of 1s2, 2s2, 2p6. On the periodic table, who has a configuration of 1s2? Who is number 2 on the periodic table? Helium. Helium is what type of element? It's a noble gas. So lithium here, by giving away its 1 electron, backed up in terms of its electron configuration, and now is isoelectronic, which means it has the same electron configuration as helium, which makes it really stable in this situation. When we look at what happened with the fluoride, it now has 10 electrons. And on the periodic table, number 10 is neon, which is also a noble gas. So by fluorine picking up that electron, it allows allows fluorine to go 1 more place to the right and achieve the same electron configuration as neon. And now we've created a very stable bond here, because both of those elements, in this case by transferring electrons, is able to both achieve noble gas configuration, which is pretty much the whole point of bonding, is for that to happen, those guys to get to that noble gas configuration. Any questions on that there? Once again, that bond is considered an ionic bond. It is held together by the opposites attract there. Oh, super zoom. There you go. Which is the electrostatic attraction. The strength of an ionic bond, or the attraction between something that is positive and negative, it does increase with increasing charge. So if you had something that's +3 and -3, much stronger attraction than +1 and -1. So it actually does increase with the charge. electrostatic attraction like that is a positive negative guy is a super strong attractive force. Very hard to actually rip apart. Let's take a look at another example. Let's take a look at calcium. Calcium there is group 2 on the periodic table, which means it should have 2 valence electrons. It also would have an electron configuration of 20, which is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. We are going to put it together with oxygen, which is group 6 on the periodic table, which will have 6 valence electrons here, and an electron configuration of 1s2, 2s2, where are we up there? 2p4 in this case. So same thing is going to happen here. We know this is an ionic bond because that is a metal. That is a non-metal oxygen. So that automatically should scream ionic to you. And that means that when the calcium gets near our oxygen here, it's going to want to get rid of its electrons. So the calcium here is going to take an electron and send it over. Out of curiosity, if it only gave away 1 electron, calcium, would it be happy? If you look at the periodic table where calcium is, here is calcium. Right next to calcium is potassium. And in group 8, before potassium is argon. If calcium gives away just 1 electron, it backs up to only potassium, which is not a noble gas. So it's definitely going to want to give away both of its electrons so that it could go 1 more step there. And that's okay because oxygen could accept both electrons. It's got a spot for both of those guys to come in. And when that happens, at that point, our calcium now will become positively charged. Our oxygen, which started with 6 electrons, will now pick up 2 more electrons. And because it picked up 2 more electrons, it will gain a -2 charge. And once again, we have formed our ionic bond here. No sharing of electrons, a complete transfer of electrons from the metal to the non-metal. At this point, what was really happening with our calcium is that is the 2 valence electrons, which it just gave away, which means when it gave it away on the other side, our calcium with the +2, 1s2, 2s2, 2p6, 3s2, 3p6, that's 18, are our good friend argon. So by giving away both electrons, it is able to achieve that noble gas configuration and be really happy. Works really nice for our oxygen because once again, in its p subshell over here, it's got room for 2 electrons. So that works out really nicely for the oxygen. When it gains those 2 electrons, the oxygen now gets 1s2, 2s2, 2p6, and now is at neon's configuration. So once again here, by calcium losing electrons, it allows it to back up to the same electron configuration as the noble gas argon. Once again, it doesn't become argon because it still has the right number of protons to be calcium, but it becomes like argon in terms of just its electrons. And oxygen, by gaining the 2 electrons, are able to move forward to the noble gas that comes right after it. And once again, it doesn't become neon. It becomes like neon in terms of its electrons. It still only has the right amount of protons for oxygen. That is really the basis of ionic bonding. And what always happens is this: the metal is always the one that gives away the electrons and becomes positive. It backs up to the noble gas that comes right before it. The non-metal always accepts the electrons and goes forward to the noble gas that comes after it. They both are able to achieve that noble gas configuration and be really, really stable in this situation. Question on that? So what happens if we kind of maybe throw together the 2 ones that we just did? Let's throw calcium in there, which again is group 2. And that is for shorthand here, argon 4s2. And let's throw it in with fluorine, which is 7 valence electrons, kind of like 9. But it has total of 9 electrons, 1s2, 2s2, 2p5 in this case. So once again, in this case, our calcium is going to want to get rid of its electrons. So we're going to see what happens here. We're going to have our calcium give away an electron over to fluorine. Fluorine is not a problem. It can accept the electron right there. Can that fluorine now accept any more electrons? It cannot. It's at 8 at this point. And that's problematic for calcium because, as we just talked about, if it just lays up 1 electron, it's only going to potassium, which doesn't have the same ring as being a noble gas, potassium. So it's not going to be very happy. So although fluorine here will be able to reach noble gas configuration, calcium cannot because of that. And what that means is we actually need not 1 fluorine here, but we need 1 more here to accommodate the second electron. And what ends up happening now is calcium now has a second spot that it could get rid of its electron. The result of this is our calcium becomes positively charged. It was able to get rid of 1 electron to each of the fluorines. Each of the fluorines will pick up 1 electron only, which means because they only picked up 1 electron, each one ends up with a -1 charge, not -2, but -1, because each one picked up just 1 electron. And there would be another one, wherever you want to draw it. I'll just draw it below it. Some people would draw it to the left of calcium, but I didn't leave a lot of room. And now what we have actually is 3 ions in this case, right, that make up this combination. And that is why when we talk about naming and we talk about putting formulas together, when you take something that is a positive and negative guy and you need to put them together, you need to put them together in the simplest way that gets the charges to 0. And in this case, we would need not 1 fluorine, but 2, gives us -2, and our +2, which gives us our proper formula of CaF2, which is our calcium fluoride formula. The real reason we tell you when we do naming and putting formulas together to make sure that it all equals 0, the charge, the real reason is this reason. It allows everybody to reach noble gas configuration when you put the charges together that equals 0 in the simplest way possible. And let's see if that is true. Our calcium here was able to get rid of both of these electrons, 1 to each of the fluorines. That means that this guy right here ends up with argon's electron configuration. Each of the fluorines pocketed 1 electron right there in the P subshell, and each of those fluorines were able to achieve 1s2, 2s2, 2p6, which is neon's configuration. So this fluorine got to neon, and this fluorine got to neon as well. So all 3 of those guys, by losing and accepting electrons, all 3 of them got to basically noble gas configuration. Do naming and formulas, positive, negative, balance it out to 0. Ultimately, what that's doing is allowing everybody to get to that stable configuration of the noble gases. Question on that there. You should, as I did there, for all 3 of those ions, they all should have charges, obviously, because this, again, is an ionic bond. Absolutely no sharing of electrons happening here. Complete transfer of electrons. Those are all held together by everybody's attraction to the opposite charges. In reality, this guy probably would find his way to that side, away from the fluorine, because they're both negatively charged. Any questions on ionic bonding and how to represent ionic bonding using Lewis dot symbols? Okay. Then we're going to move on to talking about the other type of bonding, which is clearly missed very badly in all my drawings here. Covalent bonding. So unlike, as I mentioned earlier, ionic bonding that we just talked about, covalent bonding is always between two nonmetals. And this is always where we have sharing of electrons. So as I mentioned earlier, and as we will talk about, that sharing of electrons may be equal or it may be unequal sharing. But definitely when you have some type of covalent bond, there is some aspect of sharing of electrons that is happening here. And we'll talk about how we could determine, is it equal sharing or unequal sharing here as we go through it. Gilbert Lewis suggested a role of electrons in chemical bond formation, hence the name Lewis structures, Lewis dot symbols. That's your bonding guy right there. So for example, I'm going to redo this because it got all messed up on PowerPoint here. So we'll fix it here. If we take a hydrogen guy, which has one valence electron, and we add it to another hydrogen that has one valence electron, they are both nonmetals. They clearly both have the exact same periodic trends, which means they both have the exact same feeling of either I want to give away my electrons, keep my electrons. They're identical to each other. So neither one of them is going to want to lay up their electron to somebody else and give it away. So the best that we could hope for, and the best that happens when we get two nonmetals together, because frankly, nonmetals on the periodic table are pretty much sitting in the exact same location, is that they're going to do some type of sharing. So instead of like ionic bonding that we just talked about, when we have a metal and a nonmetal, when we have our two nonmetals together, they're just going to agree upon, why don't we just share this? So we're going to share these electrons. The result of that is we get a covalent bond, where in this particular case, there is actually sharing of electrons that are happening. That's also why there is no charges here. There's been no transfer of electrons. These guys have no charges when we're dealing with this type of bonding. So how does this benefit each of them? By sharing electrons. Those electrons that are in the middle count for the hydrogen on the right. And those electrons that are in the middle also count for the hydrogen on the left. So they count for both of them. And that means that technically speaking, by sharing electrons here, each of the hydrogens have two electrons. Yes. Two electrons on the periodic table is helium. Helium is a noble gas. If you look on the periodic table, hydrogen's to the left of helium, right? Which means hydrogen, very good take-home message right here. Hydrogen only needs to get to helium to be happy, which means hydrogen should only have two electrons always, which means, let me give you some examples of things you should not do as you start drawing. Hydrogen should only be on the outside. It should either look like a one line with hydrogen or two dots on the outside, something to the left of it. If you find yourself drawing hydrogen like this and then putting dots around it, you should put a big X. It's wrong. It should never, ever, ever, one more time, ever have dots. If you feel like the dots were just not scientific enough for you and you needed to lay up like a double bond and the dots, you should put two X's on that, because that's even worse. And then my personal favorite, I'm just going to lay down everything I ever learned on this one hydrogen here. I'm going to triple bond it and put lines all over it. No, no, and no. Yes, this is exactly how hydrogen should look. One line with the H, no dots. Two dots if you're not going to use lines, because you use lines or dots, as we'll talk about in just a second here. But it should never, ever be surrounded by dots, never, ever double bonded, and never, ever triple bonded. I know it seems maybe logical, but people do it all the time. So again, if you catch yourself doing that, just put the X there yourself. Save me the trouble, right? All right. So we can represent this bonding by either the two dots like we did there, and this is basically what is referred to as a bond, or instead of the two dots, we could use one single line. So one single line represents two dots, which is referred to as a single bond. Now for bonding electrons, which is basically what these are, the electrons involved in a bond, you can use either one that you like. I personally use the lines for anyone that's in a bond like that. But some people like to use the dots. It's not wrong to do it either way. So, but I mostly will draw it with the line. So every time you see a line, it does represent two dots. There's single bonds, double bonds, and triple bonds. So every time you put a line down, it again represents basically two dots that are there. Any questions on that there? So this is basically a covalent bond, and what holds that together is those negatively charged electrons in the middle of those two atoms are going to be attracted to the nucleus of one side and also attracted to the nucleus of the other side. So it feels like a little pulling on both sides, kind of locks the electrons into place and locks the bonds together, that the electrons don't just decide to go away. Because there's that mutual attraction to the nucleuses of each of the atoms within a bond. So another example would be fluorine. If we look at fluorine, once again, fluorine is group 7 there, and it has 7 valence electrons. So again, here fluorine is a nonmetal. So once again, these guys are going to decide we will share with each other instead of obviously being transferred. Again, you can represent it one of two ways, with the dots that are the electrons between the two atoms, or again, the line, and then just use the dots for the other electrons. But once again, if we sort of count up what's happening for each of the fluorines here, the fluorine on the right there now has 2, 4, 6, 8 electrons. And again, those 2 electrons in the middle are being shared. So the fluorine on the left there now has 2, 4, 6, 8 electrons. Once again, lucky number 8 on the periodic table is our noble gases, right? Group 8, basically. And that has 8 valence electrons. So once again, here by sharing of electrons, both of the fluorines are able to achieve that noble gas configuration and end up with 8, which, as you know, hopefully, or will know, bonding 8 is a magical octet number there. Octet rule is basically the goal of everybody to get there, because the goal, again, is to become like the noble gases. Any questions on that there? Now, there are actually different types of electrons, and they're sort of identified by sort of what is happening with those electrons. So let's take a look at that here. All of the electrons here that are represented by dots, these are electrons that are not involved in bonding. I know they're not involved in bonding because, frankly, there is no letter on the other side of the dots. There's nothing there. So they are what are referred to as non-bonding electrons. Most books use non-bonding electrons these days. If you're old and decrepit like me, I use lone pairs, and some people still use lone pairs. So every time I say lone pairs, it is the same as non-bonding electrons. Those are electrons that are not involved in bonding. And again, I think nowadays a lot of books just kind of use non-bonding electrons as sort of the term, but some people still use lone pairs, and they basically mean the exact same thing. They are the electrons that are not involved in bonds. Now, there's also obviously another pair of electrons there that is involved in bonds, and that is that guy right there. And as you might imagine, it also has a very creative name. It is known as bonding electrons. Very creative. I like it. So obviously, bonding electrons are electrons that are involved in a bond. Non-bonding electrons are electrons that are not involved in a bond. And it is only the bonding electrons that you could use the line for usually. Yeah, so you can use the line for the bonding electrons only. And again, if you don't want to use the line, you can still use the dots for the bonding electrons if you prefer. But sometimes the line is good. It really makes you see which ones are being bonded. A lot of times with all the dots, you may get a little lost of where everything is, but you can do either one. You should always show all those electrons when you draw Lewis structures. You should always have the bonding electrons and the non-bonding electrons should be pictured in your picture, actually. So a Lewis structure, again, is a representation of covalent bonding. Here we show the bonding electrons with a line are dots. And again, here we are just showing the valence electrons. Each of these elements have more electrons, those core electrons, but once again, they're not involved in bonding, so obviously they're not pictured. So again, like fluorine, for example, has 7 valence electrons, but 9 total electrons. It has 2 core electrons, again, not involved in bonding and not pictured in a Lewis structure. So if we look at something like water and we draw water here, once again, water actually is sharing some electrons with 2 hydrogens, and I'll do it with all dots so we can see it. So once again, the oxygen in the middle, by sharing electrons with both hydrogens there, now is able to achieve 8 electrons, which allows the oxygen to achieve that noble gas configuration. Each of the hydrogens, by sharing with the oxygen, get 2 electrons, which, as we just talked about, is exactly what hydrogen needs. So everybody here sharing electrons, all 3 elements, the hydrogen, the oxygen, and the other hydrogen, have now all achieved that noble gas configuration, and it's very happy in that way. Just like the fluorine there, each of them are gaining 8 electrons really through sharing and reaching that noble gas configuration. Any questions on that there? That brings us to the rule that we basically been talking about, but officially speaking, the Octet Rule is the rule that says that basically everybody, again, except for hydrogen, everybody will continue to make bonds until they reach 8 valence electrons around them. As we will talk about, sometimes that just requires a single bond being made. Sometimes it requires a double bond to be made to get everybody to 8, and sometimes it requires a triple bond to get to 8. But we'll talk about when to do that and how to do that as we go through this. And then obviously hydrogen, again, as I think I emphasized enough there, hydrogen should only have 2 electrons. It really should just have 1 line to it, 1 bonding pair of electrons, and never anything more than that. And again, that also means in terms of placement of hydrogen, hydrogen should never find itself in the center of a Lewis structure, because it will definitely end up with way too many bonds to it. So hydrogen should always be on the outside of a Lewis structure. It should never be the center atom of a structure. That is also sometimes referred to the Duet Rule. And once again, the purpose of that is hydrogen just needs to get over to helium in terms of its electrons, and then it's perfectly fine and happy. So let's talk a little bit about multiple bonds. So we talked about single bonds earlier. So a single bond is represented, like I said, by 1 single line, which means 2 electrons being shared, or a pair of electrons. As I mentioned before, sometimes it requires a double bond to get there, and CO2 is an example of that. Carbon dioxide, the carbon in the middle actually needs to double bond both sides to get itself to 8. That has 4 lines drawn on. Each line is 2 electrons, so 2 times 4 is 8 electrons. The oxygen double bonded there. The 2 lines for the oxygen is 4 electrons, and the 4 dots is 8 electrons around it. Same thing for the other oxygen here. The 2 lines represent 4 electrons, and the 4 dots are the other 4 electrons. Now, all these guys here have hit 8 electrons. Once again, in this case, they had to go to a double bond to do so. Double bond represented by 2 lines, which represents 4 total electrons, or 2 pairs of electrons. And sometimes you do need to go to a triple bond to get yourself to a good situation. And nitrogen, for example, is an example of that. Nitrogen on the right, by actually sharing 6 electrons, or 3 pairs of electrons, gets to 8. And same thing here in a triple bond, 3 lines represented 6 total electrons, or 3 pairs of electrons resemble that. You usually stack the dots if you're doing some type of double or triple bond. You just don't single dot in a line, so that's not a double or a triple bond. So usually you guys stack the electrons if you're going to do that. On the bottom there, the carbon also by triple bonding and sharing with hydrogen gets to 8 electrons, and the hydrogen in each of these each get to 2 electrons by sharing those electrons with carbon. Should you double bond or triple bond out of the box? The answer is no. And people want to do it because it's like more scientific-y, I think, as well. But we're going to talk about some steps to follow when we draw Lewis structures. And if you draw the Lewis structures following our steps here that we'll talk about, it should lead you to a pretty good structure when it's all said and done. So again, I caution you about a couple of things as we go through in drawing. Don't double bond, triple bond right out of the box. And again, be careful of hydrogen. Yeah. So electronegativity is a really important sort of aspect of sharing electrons. And electronegativity is the ability of an atom to bring electrons towards itself. Write that, there you go. Ability of an atom to bring electrons towards itself. Once again, on the periodic table, increases as you go up and right, decreases as you go down, and it is our good friend fluorine that is the most electronegative element you could have. So fluorine is the most electronegative element you could have. So electronegativity really is the thing that determines, when we put two atoms together, will they share those electrons equally or will they share them unequally? So obviously, if we put together two hydrogens, we would expect obviously the hydrogen there on the right and the hydrogen on the left to basically, if my green lines here are electrons being shared, to kind of share the electrons equally between those bonds. Is basically the identical person pulling on those electrons. You can kind of think of it like that, like a rope, right? If you have the identical person on opposite sides of the rope, not much is going to happen, right? The flag, if you're doing like tug of war, is not going to move. Everything's going to be kind of shared equally. There's an equal sort of distribution of the electrons over it. And that's always what will happen whenever you have two elements that are the same and they're sharing electrons, like obviously hydrogen, like also our fluorine that we saw earlier. We would expect these guys once again to basically kind of share the electrons equally. When this occurs and we have equal sharing of electrons, this type of bond is what is referred to as a nonpolar covalent bond. And I'll be honest with you, probably most people just call it a straight up nonpolar bond. So usually somebody will just say nonpolar bond. It is a covalent bond. There's sharing of electrons. There's nice equal sharing of electrons. The result of the equal sharing of electrons is this. There is no like positive side to that bond. There's no negative side of that bond. Everything is distributed equally over it. It's kind of like a neutral bond, if you want to think about it like that. There's like no charge happening. Nice, perfect equal sharing of electrons. In this situation between these two, this would also be considered sometimes referred to as a pure covalent bond, which basically means perfect equal sharing of electrons. This is as perfect equal sharing of electrons as you could get. They both are the same element, so they're going to perfectly equally share those electrons. We will talk about nonpolar bond here in just a second. There's some degrees of equal and unequal sharing of electrons. That's maybe not perfectly equal sharing, but something like this would be perfectly equal sharing and referred to as a nonpolar covalent bond or just a nonpolar bond. Now, what happens if we kind of swap out one of the hydrogens for a fluorine? When we now put our hydrogen and fluorine together, between hydrogen and fluorine, which one is more electronegative? It is fluorine, since it is the most electronegative element we could have. So what that means is the fluorine is going to go, I would like the electrons, thank you very much. And what's going to happen is if this is all the electrons, we're pretty much going to have a majority of the electrons kind of hanging out over there on the fluorine side. Not a lot of electrons still hanging out over there on the hydrogen side. Now, there is a consequence to this. The first consequence is there's definitely unequal sharing of electrons is going to occur here. So this is going to result in unequal sharing of electrons. Also, if I have my HF and all the electrons are hanging out over there on the fluorine side, will the fluorine side be more positive or more negative? So if all the electrons decided to vacation over by fluorine, electrons are what type of charge? Which means if they all just congregated over there by fluorine, the fluorine is going to be a little bit more negative, right? Than the hydrogen, because all the electrons basically moved away, right? So all the hydrogen will be a little bit more positive. So the result of this is it creates a partially negative charge on the fluorine and a partially positive charge on the hydrogen. And that's a delta symbol, basically partially negative and partially positive. It also could be represented by an arrow, which is sometimes referred to as a dipole arrow, where it points to the more negative side, and the back part that makes like a plus sign is to the side that's more positive. That's what it's sometimes referred to as a dipole arrow. This sort of unequal sharing of electrons is another type of covalent bond, and this is what is known as a polar covalent bond, or just a polar bond. Get rid of that so you see it. So this is really a polar bond, or the official name, a polar covalent bond. And again, this is a result basically of the electrons hanging out closer to the fluorine because it's more electronegative. Why is it only a partially positive charge and a partially negative charge? Why is it not like a full positive charge and a full negative charge? In this case, they are still sharing. Yeah, so it may be unequal sharing, but there's some aspect of sharing where it's just like barely hanging on maybe, but it's still hanging on. So those electrons haven't fully moved from the hydrogen to the fluorine. And that's why it's still a covalent bond, because there's sharing, but it's unequal sharing. And that's different than the ionic bond that we talked about, where there is no possibility for sharing. They're just going to give away the electrons, and you get that full transfer of electrons that basically occur. Any questions on that there? So a polar bond is a little bit different, as I mentioned, than even a nonpolar bond. The nonpolar bond is sort of thought of as being neutral. There's no positive side or negative side, but there definitely is a positive side and negative side in a polar bond. And that makes a big difference in terms of how molecules interact if they have these type of bonds, as we'll talk about in future chapters as well. So it does make a big difference in terms of interaction and how certain molecules can interact with one another. There you go. And there's my arrow there. And again, the arrow always points to the more negative side, the one that's more electronegative within the bond, and the one that's more positive has sort of the positive side there. So to summarize the three types of bonding that we talked about, on one end of the extreme, we have an ionic bond, which is between a metal and a non-metal. And we have a transfer of electrons from the metal to the non-metal. That results in our ions being formed, our guys that have charges, our cation and our anion being formed. And once again here, as we talked about, it is that electrostatic attraction that holds that together. No sharing of electrons here. And an example would be like sodium chloride. So again, as soon as you see metal, non-metal, gonna be this situation. We get full charges occurring here because electrons are fully transferring from one to the other, like the original sort of structures we were drawing at the beginning here today. On the other end of the extreme, we have a nonpolar covalent bond, or just a nonpolar bond, if you like to call it that. That is between two nonmetals. That is going to be sharing of electrons. That is going to be equal sharing of electrons. And an example would be like our H2 or F2. Those are all examples, obviously, of that. And then sort of in the middle of the two is the polar covalent bond. Also between two nonmetals. Also sharing of electrons. But it is unequal sharing of electrons. And an example would be our guy right here, our HF. That creates, as we just talked about, a side to that bond that's more positive and a side that is more negative. It creates those partially charged parts to that bond. So on this end here, both of these are sharing of electrons. Over here, no sharing. So one end of the extreme, we got like nice, perfect equal sharing of electrons. In the middle, we have not equal sharing of electrons, but not so unequal sharing of electrons that they have transferred with the polar bonds. They're still hanging on, but not really equal at all. And then to the other end of the extreme with the ionic bond, we got a complete transfer of electrons. Nobody's hanging on to their electrons. They are moving from one to the next. Any questions on the three different types of bonding there? What we drew earlier with the Lewis dot symbols was ionic bonding, where we have the transfer of electrons. We will talk shortly here how to draw the covalent bonding with the Lewis structures, where everybody's sharing electrons. Any questions on any of that there? Okay, so how do we know, if we put two things together, whether or not we will actually get equal sharing of electrons, unequal sharing of electrons, an ionic bond? And really one of the main things that we use to help us distinguish that is electronegativity. So as I mentioned before, electronegativity is the ability of an atom to bring electrons towards itself. And it's related to electron affinity and ionization energy. And once again, we are increasing this way with fluorine being the most and decreasing this way as well. So fluorine has high electron affinity, high ionization energy, has high, too many O's there, electronegativity. Sodium is the opposite, it has low electron affinity and low ionization energy, which means, as we talked about earlier, it will give away its electrons pretty easily. And it's not really looking to gain electrons, so it will have low electronegativity. There's a guy by the name of Pauling, and Pauling came up with really a scale of electronegativity that allows you to basically put two elements together and determine whether or not the sharing of those electrons will be equal, will be unequal, or really there will be no sharing of electrons and you'll make an ionic bond. So basically Pauling said he gave values for all the elements from 0 to 4. 4 is the most electronegative. 0, not so much. That sounds scientific. Not so much there. Now, we calculate what is referred to as the change in electronegativity. That's what the delta En stands for, change in electronegativity, by basically subtracting the values for each of the elements in the bond. Like if you had two hydrogens, hydrogen minus hydrogen's value, that hydrogen fluorine, hydrogen minus fluorine's value. And if you do the subtraction and you get anywhere from 0 to 0.4 as the difference when you subtract it, that is considered a nonpolar bond, which is really a covalent bond, a nonpolar covalent bond. If you do the difference and you get above 0.4, which is like 0.5, to below 2, that is considered a polar bond, a polar covalent bond. And if you do the difference and it's above 2, and it's not perfect, this number, by the way, if it's above 2, it's ionic. And really, you don't even need the electronegativity values to determine ionic. All you need to know is I have a metal and a non-metal. It's ionic. You don't even need the numbers. You don't have to subtract anything. You should roll with ionic and be happy that that is the answer, probably. So these are sort of the cutoffs where we can use to determine it. So let's take a look at a table. Let's take a look at maybe this table here. It's got all of them on there. As we can see, as we go from left to right on the periodic table, we see an increase in electronegativity, with fluorine being the most. So for example, let us look at the three things that we just talked about, which was sodium chloride, HF, and we'll do F2. So let's say we wanted to figure out, are these bonds going to share electrons equally, unequally, or not at all sharing? We'll start with our sodium chloride. So sodium's value on the table there is 0.9. Chlorine's value there on the table, if I could see it, is 3. Thank you. So basically here, we're just going to take the larger number minus the smaller, so we get a positive number. So we're going to do the difference in electronegativity will be 3 minus 0.9. That is 2.1, yeah? So 2.1 is above 2, which tells us this is going to be an ionic bond. Once again, for something like this, you don't even need the numbers. As soon as you see sodium and chlorine, metal, non-metal, it's ionic. So if it makes you feel better, you could do that. Not all ionic bonds, when you do electronegativity difference, will get you above 2. There's some that will be less than 2. So again, I would just follow metal, non-metal, ionic, and you'll be okay. Let's take a look at HF. H is 2.1. F is 4. So when we do the difference in electronegativity here, that is 4 minus 2.1. That is 1.9 difference. Our cutoff for 1.9 tells us it is a polar bond, right? Consider the cutoff to go into ionic is above 2. How unequal of sharing of electrons is that? Pretty unequal, yeah. It's pretty much moving. Almost all of them have moved to the fluorine, but they're still hanging in there a little bit. It's very, very unequal sharing of electrons in this case, and that's why it's a polar bond. If we did fluorine and fluorine, that would be 4 and 4, which means our difference in electronegativity, 4 minus 4 is 0. A difference in electronegativity of 0 is a nonpolar bond, equal sharing of electrons. So we could use electronegativity values to help us decide how the electrons will be shared. They'll be shared equally or unequally. By the way, when you do get a difference of 0 in terms of electronegativity, that is what I was talking about earlier, is considered a pure covalent bond. That's like your perfect equal sharing of electrons. Why is perfect equal sharing of electrons versus something that has a difference of 0.4? 0.4 is still considered nonpolar, and is still considered equal sharing of electrons. But really speaking, 0.4 means there's still a little bit of unequal sharing happening there, right? But with the difference of 0, it's perfect equal sharing that occurs. So up to 0.4 is, even though technically up to 0.4 is not perfect sharing, is still considered enough to be perfect sharing and nonpolar. But definitely something of 0 is like perfect equal sharing of electrons. Any questions on that there? Why don't you try some here? Decide, is it ionic? Is it polar? Or is it nonpolar? These bonds here, let's do carbon and hydrogen. let's do potassium and bromine. Let's do carbon and oxygen bond. Let's do sulfur and oxygen. And let us do nitrogen and chlorine. For each of these bonds here, basically use the electronegativity values and determine, is it ionic, is it polar, or is it a non-polar bond? So take a couple. Okay, let's take a look, see how you're doing. So we'll start with we'll do carbon and hydrogen first. Carbon is 2.5, I believe, and hydrogen is 2.1. So again, we're just going to subtract the bigger number from the smaller to get us a positive number, and that's going to be 0.4. So with the difference of 0.4, that is polar, non-polar, ionic. That is non-polar, is really why the cutoff is 0.4, because that's pretty much the bonds we find in organic molecules, and they're non-polar. So that is why it goes up to 0.4 for that particular bond. Let's do KBr. K is 0.8. Br is that 2.8, I think. So our difference in electronegativity here is 2.8 minus 0.8. That is a 2, which will make it ionic. And really, once again here, we did not even need the numbers. Potassium is a metal. Br is a non-metal. So you could just roll with ionic without subtracting, and you would be fine. Let's do carbon oxygen next. So carbon oxygen. Carbon, once again, is 2.5. Oxygen there is 3.5, I believe. 0.5. Once again, difference in electronegativity would be 3.5 minus 2.5. That looks like a 1. That is going to mean carbon oxygen would be a polar bond, where if I drew the little arrow, it should be pointing towards which one? It should be pointing toward the one that's more electronegative, which would be the oxygen. Yeah, so it would be pointing towards that. Oxygen would be more negative in that bond, right? And the carbon there would be more partially positive, as the electrons would be moving towards the oxygen in that particular bond. If I do sulfur and oxygen, oxygen again is 3.5. Sulfur there is 2.5 as well. That is actually going to give me the same difference of 3.5 minus 2.5. Going to give me 1, and also tell me it is polar. Once again, it should be pointing towards the oxygen in this case, right? It is polar. And lastly, we have the NCl one, I believe. Nitrogen is 3. Chlorine is 3. Change in electronegativity here is 0. This is what type of bond? It is a nonpolar bond. It is 2 different elements that actually have the same electronegativity, and that can happen. So for sure, if you have 2 elements that are the same, it's going to be nonpolar, but you can also have 2 elements that are different. The reason for that is what is sometimes referred to as the diagonal rule. And that means that although, what do we do? Nitrogen is further up, fluorine is further to the right, so they cancel out their differences. They're diagonal to each other. Happens in a few places. Carbon and sulfur as well. They're not right below each other. They're kind of like 1 over to cancel each other out. So there's a few that are diagonal to each other that have basically the same electronegativity value. First off, any questions on how to do that there? Yes. Yeah. You have a similar one, I think. You have the one, I think, a couple of slides back, I think. So you have one in your book as well. I think in your book, they maybe just give you the outside ones maybe and stuff like that. So it would be provided for you if you needed it. Obviously, the values, you just need to know how to use them. Yeah. Now, do you always need the values? The answer is no, you don't always need the values. You could use the general trend in electronegativity to make a pretty educated guess. For example, the carbon and oxygen, they are in the same row here, right? and electronegativity increases to the right, which means because oxygen is further to the right, it is a safe bet that that's going to be a polar bond, with the oxygen being more electronegative. So if you're comparing two things that are in the same row, the guy further to the right will be more electronegative, and that probably will be a polar bond in most cases. In addition, if you look at sulfur and oxygen, they are in the same group. Electronegativity increases up a group, so you can make a pretty safe, educated guess that those two will result in a polar bond, with the one further up in the group being more electronegative. So if you're comparing somebody that's in the same row or the same group, you could just use the general trend, and probably 9 times out of 10, even more than that, you probably will make a correct prediction in terms of electronegativity. So you don't always need the values. You could use the general trend in electronegativity a lot of times to help you make that decision. Any questions on any of that there? Okay. And like I said, obviously these numbers would be provided for you if you needed them and stuff like that. And I think maybe in your book you have maybe something that looks like that, or one of these, I think. Yeah. So yeah, sort of, since we really don't do too much with the transition metals, a lot of times they'll cut them out and just kind of give you the sides and stuff like that. By the way, you see the noble gases there have nothing written for electronegativity values. That is because noble gases are happy, yes, and they're stable. So if you ever needed to use a value for noble gas, typically people use 0 because they're not really looking to do much. And that's why there's really no values. And that's why fluorine is the most electronegative atom that we have, because it's the furthest one to the right and up, besides the noble gases, which is next to them. So as we saw, atoms with really different electronegativities tend to form ionic bonds. That's when our metals and nonmetals get together. And atoms with very similar electronegativities will basically settle on sharing the electrons, which is what happens in a covalent bond. Either they'll share equally or they'll share unequally. And that's our breakdown, or to the 0.4, 0.5, and so forth. So let's talk now about the proper steps to follow when you want to draw a Lewis structure for a covalent molecule. And if you follow these steps, you should probably have the right molecule drawn. If you do not follow these steps and decide you want to do what I like to call piecework, which is like I'm going to draw everybody separate with all their valence electrons and try to figure out how they all come together, you'll probably end up with the wrong picture. You'll end up with too many bonds, not enough electrons. That's not the way to do it. If you follow this, this should really lead you to a path of, I probably drew a pretty good picture here. So the first really important thing is to think about logically how everything is arranged together. So to help you decide that, usually in the center of the atom, and most things that we draw here have one thing in the center and everything attached to it. Not always the case, but a lot of times that is the case. The guy in the center should always be the least electronegative atom. So the one in the center should be the least electronegative. That means that we will never find fluorine in the center because it is the most electronegative. And as our conversation earlier today about hydrogen, it will also never be in the center, correct? Never in the center, thank you. It will never be in the center either. So the least electronegative should be in the center. Really, the most important thing that you do is the next thing. You want to count up the total number of valence electrons there are in the entire compound or ion that you're drawing. That number is really important because when your picture is done, you got to have exactly that many electrons, no more, no less. Got to hit it on the nose. If it is an ion that you're drawing, you got to adjust your count for the charge. So if it is something that is positively charged, it has lost electrons. So you got to subtract that off your total. Otherwise, you'll have too many. And if it's something with a negative charge, you need to add it to your total number of valence electrons. So you end up with the correct number of electrons. Once you have done that, you got the logical arrangement, you're going to make one single bond from the center atom to each of the outside atoms. I personally will use lines to do that because they're bonds. Each line represents 2 electrons. So you're going to count up how many electrons you just used when you made the lines, and you're going to subtract off from your total. You will then have some electrons still left. Those electrons go on the outside atoms as dots, pairs of dots. until each of the outside atoms has 8 electrons, except for hydrogen, which you get no dots. And you'll keep filling up all the outside atoms until all the outside atoms have 8 electrons. If you fill up all the outside atoms and they have 8 electrons and you still have electrons to go, then they go to the center atom and you put them on the center atom as dots. So single bond, fill up all the outside atoms with dots. If you still have electrons to go, then to the center atom as pairs of dots. At that point, you should definitely be out of electrons if you put some dots on the central atom. The last thing you want to do is make sure everybody meets the octet rule. And it's this point here that if it does not meet the octet rule, then you need to fix it. And the way we fix it in this class is by making a double bond. If that doesn't fix it, we fix it by making a triple bond. Once again, here, we do not want a double bond or triple bond right out of the box. We want to save that for trying to fix things. So let's do one here together to see how we should do it. NF3. So the first thing I'm going to do here really is I'm going to count up the total number of valence electrons. So nitrogen is group 5, which means it has 5 valence electrons. There are 3 fluorines. Each fluorine is group 7, which means it has 7 valence electrons. That's like 21 and 5. I'm going to go with 26 as my total there. Yeah. Now, between nitrogen and fluorine, the least electronegative is nitrogen. It should go in the center. By the way, if you have a situation like this where you have one element and you got another element that you have 3 atoms of it, usually the one atom's in the middle, everybody else is attached to it. So the logical arrangement, nitrogen in the middle, some fluorine action on the sides. Doesn't matter if I put the fluorine on the bottom or the top. It doesn't. You can do it either way, whichever way you like. It doesn't really matter. All right, I'm going to do one single bond. I'm going to use lines to each of them. 1, 2, and 3. Each of those lines represent 2 electrons. That's 2, 4, 6, 8. Who do we appreciate? That is -6 here. That means I still have 20 electrons that I need to put on my picture. They are going to go on the outside ones until each one has 8 electrons, and they're going on as pairs. So not one at a time, but pairs. So we will do 2, 4, 6. That fills up that guy. 8, 10, 12. That fills up that guy. 14, I think. 16 and 18. That fills up that guy. At this point, I just put another 18 electrons on. I still got 2 more to go. I have nowhere to put it on the outside. Now this is where I will now go to the center atom and put it on as pairs as well. And 2 more there. I have now placed all 26 of my electrons. I want to make sure everybody is okay. And here we go. We have 2, 4, 6, 8 electrons. All the fluorines are exactly the same, so they all have 8. Nitrogen, 2, 4, 6, and 8. So everybody's good. Everybody's got 8 electrons. That would be the proper Lewis structure for NF3. This is all sharing of electrons in this deal. Yeah, everybody's sharing electrons here in this particular molecule. Question on that one there. Let's try one more here before we go. Let's do CO2, CO3, 2 minus. We'll do it together here. So once again here, this is a polyatomic ion. It has a charge. We're going to do the same thing. Carbon has 4 valence electrons, maybe 4. There we go. There are 3 oxygens, each at 6. Now the -2 here, minus means it gained electrons, and 2 is how many it gained, which means I need to add those to my count so that I'm all good. That now gives me 18, 20, 24 valence electrons. Between carbon and oxygen, who should go in the center? Carbon. Once again, oxygen should be around. I'm going to do a single bond from the carbon to the oxygen. I've used up how many electrons there? I've used up 2, 4, 6 electrons. And I wish I had my calculator, but I can go with 18. Hope for the best there. So that is 18 still to go, I think. And at this point, we're going to put those on the outside. So 2 in pairs, maybe 2. Come here. 4, 6. So that is filled. 8, 10, 12. That is filled. 14, 16, and 18. That is filled at this point. That is all 24 electrons. Is everybody good in this picture? The answer is no. Yes. Oxygens have how many electrons around them? Oxygens do have 8. 2, 4, 6, and 8. All the oxygens are identical. 2, 4, 6, 8. 2, 4, 6, 8. How many does carbon have? Yeah, 2, 4, and 6. So this did not meet the octet rule. I need to fix it. So I need to get that guy to 8. Can I just do this and put some dots in there? I cannot, because now how many total electrons do I have? I have 26, which is not 24, no matter how you want it to be 24. It is not 24. So this is a situation where we did not meet the octet rule. We want to fix it actually by trying to make a double bond to try to fix it. In this case, we could actually make the double bond at any oxygen you choose because they're all the same. So I need to make a double bond. Can I double bond the top oxygen and do this? Clearly I can't because I just did it, but should I do it? I should not, for the exact same reason. I now have 26 electrons. My oxygen up on top now has 2, 4, 6, 8, 10. Nice cheer, but way too many electrons for oxygen to have in that case. So when we go to make electrons here, we actually are going to take a pair of electrons and we're going to bring them in to make the double bond. So we're going to pull a pair of electrons in to make the double bond. When we do that, the oxygen on the top will now have a double bond and only 4 dots because I brought 2 in. Everybody else will still have the same as I originally had. And now when we look at it, we can make it all pretty and put a little bracket around it since it has a charge. Now does everybody meet the octet rule? They do. If we look at our oxygen originally, 2, 4, 6, 8. This oxygen, 2, 4, 6, 8. This oxygen, 2, 4, 6, and 8. And now the carbon, 2, 4, 6, and 8. So by making a double bond here, which is when you want to make a double bond, is to fix a problem, not out of the gate. So if by some chance that didn't fix it, I would continue to try to make double bonds by bringing electrons in to do so. If I didn't have anywhere else to make a double bond, I would bring another pair of electrons in to make a triple bond. So it works the same way. If you had to make a triple bond, you bring another pair of electrons in to make that triple bond. By doing that, it maintains our 24 electrons. Everybody has 8 valence electrons around it, and everybody is happy. Any questions on that there? All right.